All right. So what we have here is the results from all of our different simulations. All right. So this graph right here is showing the different streaks that were generated. All right. So this tallest column here represents an 8-game streak. And then this would be 9, 10, 11, 12, and so on and so forth. All right. So again, the whole purpose of this was just to kind of put streaks in context. Um, so our hypothetical team was winning 60 games. And again, 60 games not 60 games, was winning 60% of its games, which over baseball's season, which is normally 162 games, is a 97 win season. 97 wins is good, but it's certainly not exceptional. It's a good season. Most of the time, the division winner is going to have 97 or more wins. But, a good team is more up in the 100 range. So, again, 60% of your games is good, but it's not crazy. And what we saw here is that with that premise that our team would win 60% of the games, we ended up with some pretty long streaks. All right. We ended up with one streak of 18 games, three streaks of 17 games, one 16-game streak, four 15-game streaks, six 14 games, 10-13, and then 28-12, 27-11, 38-10. And in fact, if we kind of look at this in terms of the percentages, I did from 10% on up. All right. All of that added up to 29%, which means 1/3, well, not quite 1/3, but close to 1/3 of our teams ended up with a winning streak of 10 games or more. And the whole point of this is just that, when a winning streak happens, sports writers tend to lose their mind and think that something really remarkable is happening. And don't get me wrong, streaks are fun. Like it's a lot of fun to like track them, wake up the next morning, like, did it continue? Did the player get a hit? Did the team win? What's going on? Like, I'm not trying to make streaks not interesting. I'm just trying to put them in the proper context and give you sort of a better understanding of randomness. If you do something enough times, and again, there's a baseball season every year, there's 30 teams every year. So that is the exact definition of doing something enough times. You are going to get some streaks that are just random fluctuations, like flipping a coin and getting 10 heads in a row. It's not likely, but it does happen if you do something enough times. If a team went on an 18-game streak, again, everybody would be losing their collective mind. But we just saw it happen with random chance. Didn't happen a lot, but it does happen. And that's kind of the point. If you look at the history of baseball streaks, let me just bring that up quick. All right. Longest baseball streaks. All right. Again, over the 100+ years of baseball, we're not seeing a ton, but we're seeing streaks. 26, 22, 21, 21, 20, 19, 18, 17, 16. This list doesn't look that different than what we were seeing randomly, all right, with our random generation. So they happen. They're not going to happen all the time. And when they do happen, they're fun. But we also have to just be careful about putting too much meaning behind them. All right. Sometimes it's just the random fluctuations that happen when you do something over and over and over and over and over again. All right. So, anyways, that's kind of wrapping that up. As far as where we're going next, the two articles that are posted are both about parity. And parity is just another way of saying like competitive balance. Does every team have a chance to make the playoffs? Or is the league one where there's always a few good teams and then everybody else is kind of garbage? So why do we care about parity? Why does sports care about parity? A lot of it comes back to financial reasons. So, the sports leagues are trying to sell their product to an audience, and you want that audience to be as big as possible. So the longer that more teams are in contention, the more likely people are to, pay attention, follow along, watch games, support their team, whatever. You know, once your team is like, let's just say baseball because it's the longest season, once your team is like 30 games back, it's kind of hard to pay as close of attention. Same thing in basketball. If your team is at the bottom and, they're 30 games back of whoever's at the top, the Lakers or whoever it is, kind of hard to keep a lot of interest and follow your team on a nightly basis. So leagues have an interest in having things be as balanced as possible because when things are balanced, more teams are competitive, more teams are competing for playoff spots, which usually means more excitement, more things to talk about, more attention being paid to your sport overall. All right, so what we're going to do is going to focus on how we can measure parity and then looking at different things like leagues have done to try to encourage parity. So the spreadsheet you have today has a few different things going on. So there's a baseball tag, an NFL tag, and then an all 5 sports tag. So we're going to start here with the baseball tag and kind of use that as our example. And then the lab is going to involve you using the NFL and the all 5 sports tab. So what we have here are winning percentages, right, from baseball. Now, baseball has a revenue sharing system where some of the richer clubs end up paying money into a pool, and that pool gets distributed to some of the less financially well-off clubs. So that system didn't always exist, but it was created to try to generate competitive balance. It wanted to make sure that teams like the Tampa Bay Rays would be able to compete with teams like the New York Yankees. All right. Obviously, the Yankees bring in way more money, and they didn't want teams to just be able to buy victories. They wanted it to be a little more balanced. So here we have some winning percentages before revenue sharing was instituted. All right. And here we have some winning percentages after revenue sharing was instituted. So the way we're going to measure balance is with a statistic called standard deviation. All right. And you've probably heard of standard deviation before in one of your other math classes, but it's basically a measure of how spread out things are. All right. The definition I always give in my college statistics class is it's the average distance from the mean. But generally, it just tells us how spread out things are. The more spread out things are, the higher the standard deviation. The more condensed things are, the lower the standard deviation. Now, when it comes to parity, all right, a perfectly balanced league, and I'm not saying we want this, but a perfectly balanced league would be where every single team has a 500 winning percentage, right? That would be 0 standard deviation because everybody has the same exact winning percentage. Every team won half their games. Every team lost half their games. It would make for the most ridiculous tiebreaker scenario in the history of forever. Probably never going to happen, but I would just love to see how they would actually handle that if you had like every single team finishing at 500. Anyways, so that is like perfect competitive balance. All right. As things get more spread out, you end up with really, really good teams and really, really bad teams, which is going to increase your standard deviation. All right. So standard deviation is what we're going to use to measure the competitive balance in sports. All right. We're going to look at the standard deviation of the winning percentages and see, are those winning percentages condensed? Are all the teams relatively close to each other? or are they really spread out where you have really good teams and really bad teams? So what I'm going to do here is I'm just going to calculate standard deviation by hand so you can get a feel for what it actually is. But when you're doing it in the lab, you'll actually just be able to use the function that's built into Google Sheets here. All right, so as I said, standard deviation is the average distance from the mean. So what we're going to start by doing is we're going to take all of these winning percentages and we're going to subtract away the mean. All right, now the mean winning percentage is just 50% because if you average everything together, it's going to average out to 500 because you're going to have teams that are below 500, you're going to have teams that are above 500, but it'll average out to 500. So what I'm going to do is I'm just going to subtract 500 from all of these winning percentages. All right. So when I do that, you're going to see teams that are above 500, and that's a positive number. And then you're going to see teams that are below 500, and that's a negative number. Now, again, if we think of standard deviation as the average distance from the mean, right, these give us all the distances. So if we averaged these together, it would give us the average distance from the mean. Now, there's going to be a problem with that. All right, so if I take and average all of these together, I get an average of something pretty close to 0. And the only reason it's not exactly 0 is some rounding problems here that is getting rid of the accuracy. And the reason it's so close to 0 is not because this league is perfectly balanced. It's because the positives and negatives are canceling each other out. So the way we handle that is we actually take all of these values and we square them. So I take this and I square it. All right. So I'm going to drag this down. And by squaring it, that's going to get rid of all of the negatives and only give me positives. All right. So what I'm going to do now is when you calculate an average, you just add everything up and divide by how many there were. So I'm going to add all of these up. All right. And I'm going to get a number right there, 0.151846. Okay, great. There are 28 teams. Now, I'm actually not going to divide by 28. I'm going to divide by 27. All right. And that goes into kind of like more in depth than I really want to go into right now. But it deals with like biased versus unbiased parameters. And if you take a college stats class, like we talk about that a little bit. But we are going to divide by 27 instead of 28. All right. Because this is a sample, it's only one season of data. If I was using every single season ever, I wouldn't actually have to subtract 1 from my number. But because I'm using a sample, we subtract 1. That's kind of increases the value a little bit. And there's reasons for that. And then the last step is because I squared all those values, I take the square root at the end to bring it back down to its original value. All right. And I get something like 0.07499,236, right, which is my standard deviation, all right? Now, again, I just did that so you could kind of see how it's calculated. When you're doing it in the lab, all you're going to have to do is type equals STD EV, then your left parenthesis, you highlight the data, all right, you hit enter, and you're going to see that you're getting those same numbers. Again, there's a little difference here towards the end because of rounding things, but you'll effectively get the same answer. So anyways, this is sort of a measurement of how spread out the league is. Right? So what I'm going to do is I'm going to do the same thing over here. And I'm not going to go through the whole long process again. I'm just going to use the formula, STD EV. I'm going to highlight this. And I'm going to see that I'm getting 2 different numbers here. All right. So again, this is measuring how spread out things are. So the lower the number, the less spread out things are. And the less spread out things are, the higher the parity. Because remember, parity is balance. So the more balanced things are, or the higher the parity, the lower the standard deviation. So we have these winning percentages before revenue sharing, and we ended up with this value 0.075. If we round that, let me get rid of some of those decimals. All right, 0.075. And then we have our standard deviation after revenue sharing, which was 0.074. Again, probably not that big of a difference. So it might suggest that in baseball, revenue sharing didn't actually do a lot to affect the parity of the leagues. But also, you have to remember we're only looking at one year here, so it may be that it's not a perfect measurement here. But what you're going to be doing is you're going to be looking at these things, but then you're also going to take it one step further. You're going to use those same apps that we've been using before. So what you'll do is you'll take some of your data, you'll copy your data, you're going to bring it over to a standard deviation app. So I'm plugging in a bunch of standard deviations there. All right. And then I'm not plugging in standard deviations. I'm plugging in the data. Sorry. I'm plugging in the data over here. All right. I'm going to calculate the difference. And again, you're seeing those two values that we just calculated in the spreadsheet. So there's my observed difference. I'm going to do the 1,000 trials just like we've been doing. All right. And again, if your observed difference is positive, you're counting the dots greater than the value. If your observed difference is negative, you're counting the dots less than that value. So in this case, I'm counting the percentage of dots greater than or equal to 0.001. And again, that's such a small difference that I'm expecting a high p-value. All right. There's no way I'm going to be under 5% here because that difference is so tiny. And you're seeing that I am getting a high p-value of 46.7%. So I can say that, yes, the standard deviation was lower in that 1 year that we looked at, but it's not a significant difference. All right. It's so close to the year prior that we can't really say that it made a big deal one way or another. All right. So that's the sort of thing you're going to be doing. In the NFL tab, I picked some key seasons. So there's a season with no salary cap. And then there's a season, it wasn't the first year that the salary cap was instituted. I gave it like a few years so that the salary cap could really take hold and have an effect. So you've got a no salary cap season. You've got 3 or 4 years after the salary cap was instituted. And then the 2011 season is weird because there was no cap in 2010 because of like a negotiating thing. And then like the cap changed for like the 2011 season. So again, just seeing how parity, competitive balance has changed as the NFL has played around with the rules that allow teams to spend money. And then the last tab is just looking at the most recent finished season. So only complete seasons, not partial seasons, for hockey, football, basketball, baseball, and soccer, so that you can just compare parity across 5 major sports and see kind of which leagues are more balanced when we look at their winning percentages, and which leagues are less balanced when we look at their winning percentages. And then, of course, seeing whether the differences are actually significant or if they're just random fluctuations and we can't put a whole lot of meaning behind them. All right. So that's what you're going to be doing. Again, it's all this idea of kind of measuring balance between the leagues, seeing how spread out things are. And again, the higher the standard deviation, the more spread out things are, which is bad for parity. All right? That means the league isn't very balanced. The lower the standard deviation, the more condensed the teams are, which is good for balance. So we say that's a higher parity. Sometimes it's hard to keep that straight because high parity goes with low standard deviation and low parity goes with high standard deviation. So you just kind of have to remember that those are sort of opposites there. And then the rest of it works the way we've been looking at things. All right. So again, give this a shot. This is actually going to be the last sort of p-value thing we do. And then we're going to move on to a different tool that we can use to measure things in sports. All right. We're going to take a closer look at something called the z-score next. All right. So I hope this is helpful. Good luck with the lab, and we'll go from there.